To it. First part is looking at just derivatives of inverse functions. I'm going to go on this assumption that when I say the term inverse function, you don't go, huh? What are you talking about? What does it mean to be an inverse? Two functions that are inverses? Say what? Are you afraid to say it again? Give me an example of two pairs of functions that are inverses, somebody. Did you say y equals x and x equals y? That's pretty funny, actually. Well, they are inverses, but they're their own inverse, right? That function is its own inverse. Okay, what? Y equals what? I don't know. How come everybody's afraid to say it after they say it? Y equals 2x plus 1. X equals 2y plus 1, yeah. I mean, you could solve this one if you wanted, the second one. You could rearrange it so it says y equals. And if you did, you'd see why they're inverses of each other. If you take the second one and isolate it for y, it's going to say x minus 1 divided by 2. That's what y is equal to. Inverses are, this one says take a number, multiply it by 2, and then add 1, right? Take a number, multiply it by 2, add 1. This one undoes that, right? Subtract 1, then divide by 2. Just the opposite operations, right? You also have looked at what those look like on a graph. If you graph two inverse functions, they are reflections across that line right there, right? That line y equals x. That's why I said when you said y equals x and x equals y, those are inverses because you reflect that. It just is itself, right? What we're looking at now is what's the derivative of the inverse of a function and how is it related to the derivative of the original function you start with. So just so that the inverse looks, it's hard to work with straight lines. It's hard to see that they're inverses of each other. So we'll look at y equals x cubed plus 1 and its inverse. What would its inverse be? Did I write it down here anywhere? I did not write what its inverse is. What's its inverse? What's the inverse of y equals x cubed plus 1? Yeah. Let's write it down here. X cubed plus 1. If you can just see what it is, this says cube the number and then add 1. You can either just write the inverse intuitively, right? You can say if this is f of x, first of all, the notation they use is not the greatest, but it's f with the little negative 1 there. That doesn't mean to the power of negative 1. It doesn't mean reciprocal. It means inverse. You can either just do it intuitively and say, well, if I'm cubing the thing and then adding 1, the opposite of that is subtract 1 and then do the cube root. That's going to be the inverse, right? To undo those two things. Or you can write it as y equals and then switch them, right? You can switch x and y and make this. And then just isolate it, right? Move the 1 over and then do the cube root and you get this same function. So that and that are inverses. If you look at them on the graph, you see how they're related to each other. Okay, those are the two functions. This one is, that one is, if we show both of these things, we should probably make it so you can see what the equation is. Okay, so you have these two equations here. This one is x cubed plus 1. This thing on here, it's easier to say to the power of 1/3, right? Cube root is to the power of 1/3, so that's how it's entered in here. But those are inverses of each other. We want to know now, how is the derivative of the inverse, this black one, how is the derivative of that inverse related to the derivative of the original function? So let's first see what it's asking you to find here. Number one, we have to be okay with the last concept here, which is if that point is on the graph of the original function, that point is on the inverse, right? Why does that work? Because it is. Yeah, I mean, if you take a 1 and you put it into that function f, you get a 2, right? So it makes sense that to go backwards, you put it in the inverse function and you get that number back, right? The inverse function just undoes what you did. It goes back, takes the result and gives you back the original value. If you're asked to find this now, the notation is not, if we move this, If we try moving this again. This notation here, if you're asked that, what does that mean? Looks kind of crazy, but what does it mean? D dx derivative of the inverse. And what does this 2 right beside it here mean? At 2, right? You could also say it like, you could say this. Derivative of the inverse evaluated at x equals 2. You could do that, or at 2, right? So if you want words here, it means derivative, it means derivative of, oh, come on. Try again here. Derivative of inverse at 2. Okay, derivative of the inverse at 2. So let's look back at the graph and see what it is here. Derivative of the inverse, we want the tangent line right there, right? That's the derivative at 2, okay? If you slide this around here, that thing, all you want is you want the slope of the inverse. How's it going to be related to the slope of this curve? How can we find it using this? I know you could just find it from that by just doing the derivative implicitly. There's nothing wrong with that. But I want you to know the relationship between the slope on this curve and the slope on this curve. Where can I find a slope that's related to this one? At 1. Why is it here? Why is the slope at 2 on this curve connected to the slope at 1 on that curve? Yeah, that's the point that corresponds, right? That corresponding point, so it's not at the same value, it's at the corresponding point over there. Those two slopes are related to each other. If I move this one, okay, those slopes, you see how they're related? Like the slopes are reflections as well, right? If you reflect that slope, what do you get? If the slope of this one was, if the slope on the original curve was 3, what's the slope of this 1 over 3, right? Which is over here, 1/3. As this one gets flatter, the other one gets steeper, right? So if you stop where this is about 5 or something, I don't know if I can stop exactly at 5, pretty close. Slope of that one is 5, slope of this one is 1/5, right? Those are reciprocals of each other. Okay, now I know it's complicated when you start talking about this. The derivatives of inverse functions are related because they're reciprocals, to further confuse, because in grade 12 we get mixed up between reciprocals and inverses. The relationship between the derivatives is they're reciprocals of each other. Not at the same value, at the corresponding value. All right? The steeper this one gets, the flatter the other one gets, and so on, right? So if you kind of just keep that picture in mind. If you want to find the derivative of the inverse at 2, okay, and we saw that it was 1/3, right? Wasn't it 1/3? If you want to find the derivative of the inverse at 2, you can just find the derivative of the inverse using implicit differentiation. Why can't I move that thing? So you can either take the inverse, which was, what was the inverse? What do we say the inverse was? I just moved it. Cube root of x minus 1. You can find the derivative of that thing, right? That's the inverse function. You can find the derivative of it. What's the derivative of that? How do you do the derivative of that? You have to use the chain rule. You might want to write it like this first. Might be easier. To the power of 1/3, and then use the power rule for the outside function. So that's just rewriting it, right? That's rewriting it as a power. So you can use a power rule. What do we have then? We have 1/3 that inside the bracket. What do I do with the power? -2/3, subtract 1, right? But then I got to times the derivative of the inside. What's the derivative of the inside? Just 1, right? So you don't have to actually multiply by 1. If you want to write it in terms of using a square root, so it kind of matches the original function. It doesn't look all that great. 1 over 3, and then this is on the bottom as well, right? And this is the cube root of x minus 1 squared. That's the derivative. You could also find, and then you can sub the value in, right? So if you want the derivative of the inverse at 2, and then you could sub in 2 there. Does it work? What do we get if we sub in 2? We remember we got to try and aim for it to be 1/3. We saw on the graph that it should be 1/3. If I sub in a 2 there, 1 over 3 times cube root of 1. 2 minus 1, 1. 2 minus 1, 1 squared is 1, right? Cube root of 1 is 1. It does equal 1/3. Sometimes it's easier to work with the original function, though. What else could we have done knowing the relationship between the two? What else could we have done knowing how these two things are related to each other? Knowing the connection between these two? If we want the derivative of the inverse at 2, what could we have done instead using the original function? You could have found the derivative at 1, right? The original function, find the derivative at 1 and then do the reciprocal, right? Instead. Now I have not left myself nearly enough room here. Hopefully you can fit it in. We'll do this in pink. So it's such a revolutionary concept here. Or just find derivative of the original function at x equals 1 and take the reciprocal, right? This is not something you're going to use that often, but it's a relationship that's worth knowing, right? What was the original function? Y equals x cubed plus 1. The derivative is really easy to write. 3x squared. So y prime at 1, right, is 3 times 1 squared. And that gives us 3, right? Remember, it's not going to be the same. It's going to be the reciprocal. Therefore, derivative of the inverse is 1 over 3, right? Remember, those are reciprocals. I guess I should have said that 2 is 1/3. This is derivative of the original function, right? Derivative of f at 1 is 3, so derivative of the inverse is 1/3. Reciprocals, right? That's the relationship between the two, right? Those are reciprocals. Just because of the symmetry in the graph when you reflect it, right? When you reflect something over that diagonal line, all the values switch, so the rise becomes the run becomes the rise, right? The slope is going to be reversed like that. If it was 3 over 1, now it's 1 over 3. The notation for this, I think this is a good one to write with words. If you try to write it with symbols, it starts to look pretty complicated with all these ddx of f to the -1 and values and things. Think about what these values are. This was the x value of the original function. This was the y value of the original function, right? I think the best thing to do, write it in words there as the shortcut. If you want to write something in here, you can. The derivative of the inverse at x, okay, is I think it's better to call it a and b, to call the point that you're looking at. So let me write it down here first. I would call it a and b. So we had something like this, right? We had a function that looked something like that, and the original one looked like, no, it didn't look like that. Looked like that, and the inverse was over here. Why am I even bothering trying to do that? We have the technology to take a picture. Okay, so if you label that picture or use that as something to write the rule from here. If this were now instead just called A and B, this one's going to be called BA, right? The derivative of F inverse at B equals 1 over derivative of F at A if AB is on F, right? If the A and the B go together. In the textbook, they call it A and F of A. Like if you look at the definition, or if you look at this in the textbook, it says, it calls the point A and F of A, but it ends up, I mean, it's the same thing, because then here it just says, thanks, it just says F of A instead of B. It says derivative of F at F of A. I tend to think people get it more if you just say if AB is a point on the original function, this is the reciprocal of this. If you try to write this in symbols, you can, right? If you want to write it in that box up above, you could say F inverse at B prime. See, when you already have this F inverse in here, it's hard to put a prime as well. That's why they're using the d dx. That's why they were using this notation. Derivative of the inverse at B is 1 over the derivative of the original function at A, if AB is a point together. In the textbook, they call B F of A, or they call A something else, but I think that's the best way to write it. And just put if AB is a point on there. Is that clear? Very clear? 17 minutes and 51 seconds later. What's that? Clear as mud.
What do we put in the little box then? So is it
I would put this, and then just put if. It's a very large box, isn't it? If A.
No, not that box.
I know the box. I know the box. Doesn't it say there? What's the derivative of this? Let's go back up to the box here. If you want the derivative of the inverse, it's I would write it the way I just wrote it out down there, and maybe make your own box because you're not going to fit it in there. Just make a bigger box over here. I didn't really think carefully about how big that box needed to be. The time when this would be useful is if you want a derivative of something that's going to be a really ugly function when you try and turn it around, or if you can't even turn it around at all, right? If you can't solve this for y if you do the inverse, right? If you do the inverse of that function and try and solve it for y. If you want each of these things here, it's easy to write the derivative of the original function, right? There's the original function. So f at 1 is easy. It's just 1 cubed plus 1 squared plus 1, right? It's 3. Whoops. If you want f inverse down here, okay, if you want f inverse at 3, you can switch it around and sub the numbers in. What would the inverse function of that be? Well, actually, you can just use what we just found, right? What's f inverse at 3? If 1 gives you 3 here, if I do a f inverse of 3, what's it going to give me? 1, right? You can just do it from that. You can work backwards. It's easier to work with this than trying to turn it around. If you turn it around, you get x equals y cubed plus y squared plus 1. You can't solve that for y explicitly, right? You could go through and do the derivative of that implicitly. It's a lot of work, right? The derivative of the original function is easy, right? Y prime is just, or f prime at 1. Let's do it x first. 3x squared plus 2x. So f prime at 1 is just 3 times 1 squared plus 2 times 1. Or in other words, it's 5, right? So you have this point 1, 3. Slope of f at 1, 3 equals 5. So what does that tell us about the inverse here? Slope of f inverse at what point? 3, 1 equals what's going to be? 1 over 5. When you work with a situation, it's a lot easier than trying to write it in general terms. So if you want f inverse prime, if you want the derivative at 3, okay, derivative at 3 here is just 1/5. I mean, this question is set up to just ask about this, right? But f inverse prime at 3 equals 1/5. Okay, it's just saying this, that are reciprocals of each other. That's probably as much as you're going to want to ever know about that.